Good evening, everyone. Morning or afternoon. Greetings today, wherever you are. And of course, Kalisperas to our Greek attendees. I'm Divik. I'm the sub-chair of BTSYM, who oversees the professional development subgroup. Welcome to this workshop organized jointly by British Tunneling Society Young Members and the Greek Tunneling Society Young Members Group. Your interest and presence truly reflects the resilient nature of our industry. It reinforces that professionals working within our underground space do not allow constraints to hamper progress and find alternate approaches to ensure achievement of our combined goals. So please accept my gratitude for showing interest in attending what is not only the first ever purely online BTSYM workshop, but also is the first ever international collaboration by BTSYM at this scale. To aid smooth running of the workshop, I would like to remind you of the guidance circulated as a part of the joining instructions. Please ensure your microphone is muted and your webcam is switched off during the course of this workshop. Please feel free to use the chat feature to ask questions or catch the speaker's attention. However, please don't use it for non-workshop related discussions. In case Microsoft Teams allows you to use the raise hand feature, which is a new feature they have added, you can use it to catch the speaker's attention too. For the safety of your IT infrastructure, we advise you not to post any files or links within the chat section or click on any files or links within the chat section either. Sorry, just bear with me for a second. Okay. So yeah, I was saying, please don't click on any links shared within the chat feature. Also, please don't unmute your microphone unless you're requested by the speaker to do so. Once you have provided verbal input, please ensure you mute your microphone again. Finally, I would like to remind you that this workshop is being recorded as well as streamed live on YouTube. Your attendance, therefore, implies you do not object to this. But given it's a lot of first we are dealing with here, I hope you'll forgive us for any technical glitches or slightly constrained ease of interaction during the course of this workshop. To continue supporting industry professionals in their early careers, we do plan to run similar events in the coming months, some with other young member groups. So please keep an eye out for these on our social media accounts and of course on our YouTube channel. Our YouTube channel also contains recordings of our lectures from over the past 2 years, so please do check it out. And if possible, please subscribe to it as well. Also, if you press the bell icon after subscribing, you will receive notification of future live streams that are planned. Finally, remaining mindful of the less than ideal circumstances that currently exist globally, we are extremely grateful to our Greek counterparts and today's speakers, of course, for agreeing to deliver the workshop online. We also hope our collaboration will continue, and we look forward to the day the world gets back to normal so we can host you in person at the Institution of Civil Engineers and treat you with our traditional BTS chips and sausage and post-lecture drinks. On that note, I'll transfer the baton over to Dimitrios to continue today's proceedings and introduce GTSYM as well as our speakers.
Thank you, Divik. Good afternoon from UK. I ought to say in Greek as well, so Kalisperas olus. So before starting the introduction of our two invited speakers, I ought to say, as national representative of the Greek Tunneling Society, the Young Members Group, a big thanks to Divik and generally speaking to the steering board of the British Tunneling Society Young Members Group, who gave us the opportunity to co-organize this event. And a special thanks to George Dulkas, who chased it and made it happen. Now I'm in this interesting position, I would say, to introduce these two persons who 5-10 years ago in my undergraduate or postgraduate studies, they were my supervisors in several courses. But okay, we are getting older. So I would start with alphabetically with Andreas. So Dr. Andreas Benardos is an associate professor at the School of Mining and Metallurgical Engineering of the National Technical University of Athens. He holds a diploma in mining engineering, a PhD in risk assessment for underground construction projects from National Technical University of Athens. His research interests are focused on the topics of underground space development and mine design, risk assessment and uncertainty in underground construction, project cost estimation, as well as on application of artificial neural networks in geoengineering. He is currently the director of the interdisciplinary postgraduate studies, design and construction of underground works of National Technical University of Athens. He has participated in more than 25 research projects awarded by European and national bodies and private firms, and has published more than 70 papers in scientific journals and international conferences. And now I will follow with Vasilis Marinos. So Dr. Vasilis Marinos is an associate professor of the Aristotle University of Thessaloniki and recently elected in the National Technical University of Athens in the Civil Engineering Department. Well done, Vasilis. He is the vice president of IAEG 2019-2022. He has published more than 100 papers in the national journals and international conferences. His area of expertise includes engineering geology in tunneling, geotechnical classification of weak and complex rock masses, and tunnel geotechnical databases. He has been awarded from the IAEG with a runner-up certificate of Richard Walters Prize. He has been an invited speaker in a number of conferences and has actively participated in the organizing committee of international and national conferences. So this is it from me. The stage is yours.
So good evening, everybody. Dimitris, Andreas, or I should start first? What's the plan?
Vasilis, I think that you should start first.
Okay. So, good evening, everybody. Dear colleagues, dear friends. I thank you very, very much for the invitation. British Tunneling Society, the young members, but also the Greek Tunneling Society. I hope that you can see my screen, so please let's have a positive reply by a microphone by Dimitris that everything runs okay, so I can proceed. Dimitris, is it okay? My first slide, can you see that?
I think so, yes.
Okay, that's great. So in my presentation, I will focus mainly from the uncertainty that comes in tunneling design and construction from the geological material. And I will focus mainly on rock masses in different geological environments from the experiences coming from the design and construction of many tunnels in northern Greece. So a word that we usually say about uncertainty, and this is a more recent word, uncertainty we use. We used to say more like a challenge. So when you hear that this is challenging and this is a challenging work, and it means something, it is difficult to evaluate, difficult maybe to describe it, difficult to design it, or difficult to construct it. And this challenge is due to this hybrid zone of an orthodox synergy between geology and mechanics, and in tunneling particularly, rather than any other types of geotechnical practice. And of course, this challenge and this uncertainty that we have to reduce it, but also this magic of prognosis by this stochastic organization of all the methods of geology and the diagnosis of geotechnical problems comes from all this particular uncertainty in tunneling. So some codes that has to they describe in this uncertainty is coming from the Carl Terzaghi, from his Harvard lecture notes. And Terzaghi, though father of geotechnical engineering, he used to teach engineering geology in his last years of as a professor. So he says here that tunneling is at the borderline between geology and engineering. And teaching engineering geology in his last years, he particularly highlights this. And another quote that it's particularly true, I don't know who said that, so excuse me about that, but even being a young tunnel engineer, you already know that the tunnel is defined as an underground work, at one end of which an engineering heart beats, and at the other a lawyer is rubbing up his hands. And you know that in many, many cases, many claims are lying down and are depending on these geological and engineering geological particularities that you may meet along the tunnel. So the outline of my presentation first is to give the general concept and define the framework where my presentation is focused. And of course, I will focus on the engineering geological particularities and where it's involved towards the geotechnical design. And I will focus, I will give a special emphasis on the prediction of the tunnel behavior and the assessment of the immediate support measures. And I will give, of course, many case studies and step-by-step example from how from the geological model to the rock mass model and the tunnel behavior types can be evaluated. And some words about the principle of the immediate support measures, but again, as a concept, as a type, coming from this assessment of the behavior types of the tunnel behavior mechanism. And of course, I will end with my conclusions. So the framework of, in general, engineering geology, uncertainty, and tunnels would say that, first of all, we have to build a geological model, and the consideration to find all these particularities along the tunnel, all these geohazards that may come, and either it is the lithotypes, or the tectonism, or the weathering, or the paleogeographic evolution, and all this should be constructed in an engineering geological model of the area. So a lot of uncertainties may arise from that appreciation. And then in order to put that in the scale of your section, of your channel section, the identification of the ground mass types, either it's a soil or a rock, and specify all these engineering geological characteristics keys that they affect the tunnel stability or instability. Then the assessment of the engineering geological behavior for every ground type when unsupported before implementing any support categories is another issue that is being examined here and analyzed. The selection of the definition of the appropriate design parameters that the geotechnical engineer requires for his analysis is a particular assistance of the engineering geologist towards all these tunnel design efforts. And finally, the principles of the excavation and immediate support measures based on these failure modes. So I'm not talking about a detailed support measures here, but just the principles, the types that the engineer should be focused in his analysis. So in general, we know that when we are taught in our studies that the assessment for ground and design for tunnel or for any geotechnical works comes from the geological model, and we should translate all this history towards properties and going from the scales of many kilometers to the scales of a few meters maybe. So from the geological model to the rock mass model, and according to then the stress regime and the groundwater regime and any other boundary conditions, then we have to select some geotechnical parameters and the appropriate criteria in order to go to the design and the construction. So this is a straightforward, let's say, line of action. But I had to emphasize here, what about the assessment of the tunnel behavior towards the geotechnical design? So the simple questions, how the ground works, how this is implemented toward all these steps. So I would like to emphasize here and to provide this flowchart in order to emphasize that the main link from the definition of the ground types to the selection of the excavation and support categories, it is the definition of the rock mass or the soil behavior types in tunneling. So let's see that in a little bit detail. So from, of course, the geological model and the principal information from the lithology, the tectonism, the structure, the weathering, hydrogeology, any evolution can have the material and can affect its properties, either it is an intrinsic or a structural material. Then we have to identify all the basic principal geoengineering keys that characterize the rock mass behavior in tunneling. Excuse me, I use the rock mass behavior, but you can say ground behavior in general here. Just my examples will be given in ground types, in rock mass types. That's why I use rock mass types. But it's the same framework for general for soil types. So we have to define the rock mass types along the tunnel, of course. And then, according to the rock mass and discontinuity characteristics, the in situ stresses and hydrogeological regime and the tunnel geometry, then we can proceed to the definition of the rock mass behavior types in tunneling. And then we can be a better, let's say, we are on a better ground in order to select the appropriate design parameters and give a more realistic analysis. Either it is a stress control or a structurally controlled failures, and then provide the types of the temporary support measures, the principles, not the detailed analysis that comes afterwards by the geotechnical engineering, but just the principles and the types of the support that he should be focused on in order to face that failure mode. And of course, then the contractor documents that follow. So the first step is coming from all this. You can see the scale up there that we can never design in this large scale, but here you can see that we have to detect a pin in our mountain and to see what is the structure, if we have mixed conditions, what is the tectonism, what is the weathering degree, and all this. Try to put that in our mountain in all the boundary conditions and in situ stresses or hydrogeological conditions we may have. So the definition of the rock mass types is the first step in this design. This is, let's say, if we delay our design in tunneling to our final submission in our design, what he may need during this time, he says, give me in a table the rock mass properties, the soil properties. Give me the section and the properties. This is a reality. This is what the geotechnical engineering wants. Of course, this should not be the only, let's say, information that we passing by to the geotechnical engineering. But let's categorize that at first, and we will see how we can assist by not only providing this sum of properties. So the definition of rock mass types, of course, is a sum of geomaterials with similar mechanical, physical, and hydraulic parameters. Okay, this is a definition, and of course, the number of these depends on the in situ geological conditions, and of course, to the excavation method also. Then we can say that we can put that, we can group that we have to detect the properties of the intake rock and of the rock mass. So any strength and deformability parameters of the intake rock, of the rock mass is of higher importance. And of course, the strength of the discontinuities and any other geometrical characteristics of the discontinuities are of great importance, depending again, of course, of the behavior of the material. So let's see an example here. For example, coming from the Athens metro, you can see here a very nice geological section, but of course we cannot just stay there. We have somehow to quantify all these different units we see in this sketch, in this drawing, and we have a number of boreholes to do that at first. So we first go into the geological formations. We say, okay, these are alluvial deposits, and this is the rock mass unit. In this particular case, it's called an Athens schist, an upper unit. Okay, this is an example. You don't have to know about that. Again, we have to distinguish then which rock types we have, or which more particular units. So we can isolate, we can detect meta-sandstone in one case, and alternations of meta-siltstone and meta-sandstone. Within these alternations, we see which one prevails or not. Okay, so we have to do this distinction in rock mass units, and then we can take different kind of specimens of samples and trying to test them. And again, we have to put some, we have to use some common language between the geologists, engineering geologists, and the geotechnical engineers in order trying to describe these materials. And when this is a weak rock mass, then here, for example, in alternations, this is a kind of fleece. They use the GSI for heterogeneous rock masses like fleece, and you see for hundreds of cores, they do this kind of geotechnical classification, and you see from the bubbles all these areas that you may have in your rock mass qualities. So here, immediately you can have a description of your rock mass, and you can quantify, you can put some numbers in material, or just to classify, just to characterize, in order to have a common language. Together with the laboratory tests, if it's a uniaxial compressive strength, and information about the deformation modulus of the intact rock, also from point load tests, you can come up from correlations, and you can say that all laboratory and in situ tests correspond to one of the rock mass types and are evaluated according to their nature. And you can start translating this previous structure, previous nice geological sections to this. And you can put some numbers to that. Either it is a rock mass, of course, a classification value, and other properties of the intact rock. So this is an example of how you can identify rock mass types using the rock mass classification system and the laboratory test. Another issue that we should be very, very careful when we're identifying the rock mass types and then evaluating their behavior in tunneling is a scale. So this is a very famous sketch by Hook, and you can see either it is an open pit or a tunnel in your left hand. The scale of your construction is influencing the rock mass type. And I don't have to explain that and lose time. Many of you should know that, but you can see it can start from an intact rock, or a blocky, or a very blocky, or heavily blocky material. So it comes to a totally different appreciation of its properties and its description in a quantitative and a qualitative manner. So here, for example, in an open pit, you can see that when you examine in a bend scale, or this can be a small tunnel, for example, you can see that in the first scale, in the bend scale, we may have a structurally controlled failure. So all your rock mass type, let's say your ground type parameters are focusing, and all your site investigation should be focused there, and on the geometry of these planes, on the shear strength of these planes. So it is completely anisotropical behavior. But when you're going in the same open pit to analyze in another scale, so an overall stability, then this material can be a Hook and Brown material. So it can behave isotropically. So all the other parameters can, from the Hook and Brown, can come and assist in order to try to describe its properties, and then use all these parameters for your analysis. Of course, again, I have to apply that this is for isotropical behavior. So we know that as a very large description, isotropical and anisotropical behavior. So here in this presentation, I want to highlight that, and not just depend on a rock mass classification system. So, but let's see that in afterwards. There are some very simply data entry stream for using this Hook and Brown system and how you can evaluate GSI. I'm not gonna stay here long, but let's see these simple slides here. The uncertainty. So in the x-axis, you can say you can see the MI property, the constant MI of the Hook and Brown, and in the y-axis you can see the uniaxial compressive strength, and you can see the ranges. And within the chart, you can see within this diagram, you can see different kind of geological materials: gneiss, granites, ophiolites, limestones, Flysch deposits, cysts. And you can see in these bubbles, these numbers inside the GSI charts, you can see all these ranges you may have according to the tectonism, according to the weathering. So if you put that in correlation also with the other Hook and Brown parameters, you can see that uncertainty that can arise from your material. So why select a property from a table from the literature of the MI? You can see the ranges you may have that can give you big ranges also in your results. So this is a very, very detailed job that should be done with triaxial tests for the calculation of MI and for uniaxial compressive strength of point load for your materials, and of course the GSI that can come for the site-specific, let's say, rock mass. So in order to select, let's say, a geotechnical classification system, you should be aware of the application ranges you have to, when you use that. Again, of course, other equations that you can use in order to calculate deformation modulus, because when you want numbers and you need to provide that for your rock mass, then you can use that these correlations that may come from previous experience. And then again, it is your material. Either it is in the intact rock, like the deformation modulus of the intact rock, or the modulus ratio, or it is the uniaxial compressive strength of the intact rock, and of course the rock mass classification value. So let's proceed to the main, let's say, scope of this lecture: understanding the behavior in tunneling. And when I say understanding the behavior, I mean mainly the importance and how this should be incorporated in the geotechnical analysis. So Peter Vaughan, in his 34th ranking lecture, the understanding of real behavior is more important than accurate calculation, and better prediction is only possible when reality is modeled. And by Hook and Lons in 1974, previously, the function of rock mechanics engineers is not to compute accurately, but to judge soundly. And when all your analysis is based in a more realistic modeling and the appreciation of how the ground works, then your job is founded in more sound ground. So let me say here first, before proceeding, that of course we have different excavation methods, but here I will focus on the conventional tunneling methods and from where my examples are coming from. So I will focus in the conventional tunneling, and here are, let's say, 99% of our examples coming from sequential excavation and top heading and bends method. So not about full face excavation. And we're gonna talk about all these measures we implement in such excavation methods, and it's not in the scope of this presentation to analyze that. And I would say that most of you know about all these. So when we're gonna put them, and what kind of measures we select, and they're let's say heavy grade of the support we're gonna use and the type, again, this depends on the appreciation of the behavior before applying this. And I can show that by illustrating this example. So imagine you have these two different rock mass types. The first one on your left is a fracture rock mass with poor discontinuity surface conditions. Let's say we have siliconite surfaces under low tunnel cover. And on the right side, we have a brecciated rock mass with good discontinuity surface conditions, like rough surfaces under, again, the low tunnel cover. So we have the same kind of material. Let's say this is a limestone and the same in situ stress regime. And when we use the GSI system and the observational chart, and it's the same if you use the quantified chart, it's the same, absolutely the same. We will see that the first rock on your left, it will be projected here in the diagonal of 40 by blocky and poor combination. And on the right side, it will be projected again in the diagonal of the value of 40, though it is a very poor disintegrated rock mass with good rough surfaces. If you do that, if you go and calculate your properties by the Hook and Brown failure criteria, you will find equal rock mass strength, cohesion and angle of friction, and deformation properties, and equivalent estimated shear failures from a numerical analysis. So you will have equal analysis for both rock masses if the structure is not considered, but only the classification rating. And if you do that for the RMR system, again, you will find yourself in the same support category, like here 3, for example. So you will get equal suggestions for support measures. But the actual tunnel failure mechanism and appropriate support measures are totally different. So in the left side, we will have wet failure and block failure along the siliconite surfaces. And this will probably, it will happen very fast because you have a low friction along that. So you're thinking about a specific kind of supporting your anchors. So like swellers or split types, in order to immediately support and confine these blocks that you can analyze in your tunnel design. And on the right side, you may have a flowing ground or raveling ground, depending on the groundwater presence. And here you probably need a pre-support by light focal umbrella-like spiles, or a very small excavation step if you don't want to do that. And you can see different kinds of appreciation in your support measures. And all these here are, of course, not any, let's say, suggestions of detailed support measures. Of course, its experience is coming from many tunnels, but I wanted to highlight the type of support and the philosophy after identifying the failure mechanism. So we can identify the structurally controlled failures and wet sliding or chimney type failures or cone failures you may find in the literature, raveling ground or flowing ground. And there's then the stress control failures of small to medium deformations. So we have shear failures in a shallow perimeter around the tunnel. And squeezing ground, of course, is the more severe expression of these stress control failures. And of course, the brittle failure and the rock burst or spalling we may have. And the tunnel face instabilities, of course, again, we may have a phase extrusion in rock masses with very low mechanical parameters in depths, and block sliding along joints of favorable geometry and strength. So you can see here all these different kinds of failures that, again, here, this is a classification of different kinds of failure modes in your tunneling, in your conventional tunneling. And you can see from the stable conditions, of course, you can identify that a tunnel behavior, so I prefer to say tunnel behavior than failure modes, because you may have stability. So in general, the behavior types coming from stable or brittle failure or red type failure, and you can see the different kinds of conditions in your material that you can have these failures. I'm not gonna stay here and make a theoretical example of that. but I will show some examples later in different rock masses. And again, raveling, flowing ground, and then going to the shear failures around the perimeter. And of course, some particular behaviors like swelling or some anisotropical strains around the tunnel. And again, I have to highlight, again, to emphasize that, again, this is some examples, some classification of the failure modes. And in your site specific, in your specific tunnel, you should identify your failure modes, of course, in correlations with other examples in the literature. So some pictures from raveling ground or wedge falling and sliding, and chimney type failure, and you see here in the material that has over excavated and fallen. In this particular case, this is a completely weathered gneiss in depth along a fault zone, and of course the squeezing ground and overstressed still sets. You can see here how all these are yielded, and the very famous picture on the right side. Again, you can see in a hydraulic tunnel how this has squeezed. And a first approach in order to say, let's say, when we start to have these stress control failures, it is this chart coming from Hook and Marinos 2000. From many cases, and the appreciation and the evaluation of the rock mass strength to the in situ stresses can give you the severity of this squeezing, and different cases from around the globe, and all this monitoring that comes from all that tunnel gave this chart. So we can have the calculation, the first approach. This is not a detail, just to say that in this section of our tunnel, we may face this kind of severity in our stress control problems. So from 62 tunnels, this experience coming from the design, 62 twin tunnels, I have to emphasize, we have the prediction of the tunnel behavior, either by identifying let's say parameters. The first one is the structure, and it is this nice blocks here, these nice sketches from the geoside chart, the well-known, and then two sets of columns, the small overburden on your left and the large overburden on the right, and the low uniaxial compressive strength on the left and the high uniaxial compressive strength on the right. And the limits come low, high. It is depicted here, and you can see that either we are shifting from a non-stress control problem to a stress control problem that has to do with this ratio of the uniaxial compressive strength of the rock mass to the in situ stresses. So in the combination of the geosize, of the uniaxial compressive strength of the intact rock, and of course the overburden, can shift you from a non-stress control problem to a stress control problem. That's why you may see a wedge problem in the left, but then becoming a shear problem on your right, shear stresses control problems around your tunnel. So another, let's say, boundary for the gravity-driven problems has to do with the situation of confinement. So when we are in depth, we have some confinement. So maybe some crown failures we may have, or some raveling ground we may have close to the surface, where we don't have a lot of confinement, we may not have it in depth. So when we get from raveling ground, you can see in situation 18, we may not have that in depth after, let's say, 70 meters, and we may have chimney type failures. And of course, we may have some initiation of stress control failures. I'm not gonna say more in this chart because we're gonna use that in our examples later. So let's proceed to these examples and case studies. So we have different environments here, and you can see, let's give a very, very rough introduction of this project, which is running with a direction west to south, west to east, connecting the Europe with the Asia. So this has been a very, very important project for Europe in the previous decades, and it's already constructed. So you can see how characteristics and the overburden reaching here up to 600 meters, and you can see the cross sections reaching to 120 cubic meters, square meters, sorry, and the lengths. You can see that all these 62 tunnels are bore tunnels, and more are cut and cover or cover and cut are other tunnels. Many of them in a mountain environment. You may have combined Greece and in your mind as a country with a lot of sea, and this is particularly true, but we have a lot of mountains, and our alpine chains are very, very challenging. And this is a road coming from the Roman times called Via Egnatia, and part of it ran along this old ancient road. What is particularly important here, and we were very, very lucky when we had to construct these tunnels, is that you can see the geology of Greece with its main geotectonic units running from the north to the south. So we cut almost all of them perpendicularly. In this case, we had a lot of information about Flysch formations, molasses deposits, crystallic rocks, weak cysts, many rock masses. I can hear a microphone. Okay, this is mute. Okay, and all this information were incorporated, analyzed in a database, in a tunnel information analysis system with that manages and correlates all the site investigation, all the parameters, all the excavation and support categories, all the analysis, and of course the construction records and the cost of these tunnels. So a lot of information coming from many tables that were afterwards correlated, and you can see here the structure of this database, which was based in also in the AGS database of the Association of Geotechnical Specialists. So let's go to our examples. And our first example coming from limestone. So this is a straightforward material, of course. Not a lot of challenges in limestones, only when karstified or heavily brecciated. So this is a case where you can see this kind of structure, and our tunnels running along this big tectonic line, this fault. So we had a brecciation, not just in a small zone, but in the scale of napes. So we had this brecciation along our hills. We were digging our material. And you can see in the slopes, excuse me for these pictures, it was in my youth when I was not considering my safety first. And so this is not an example for the young engineering geologists and young geotechnical engineers, tunnels, sitting there without any helmet. So excuse me about this photo, but I want to highlight here how they stand. They have very good frictional strength, this material, but very low cohesion. So in open cuts, they may have a very good stability. Of course, they have some cementation and have cohesion also, not only to frictional strength. This can stand. But depending on this interlocking, we may have some raveling ground within the tunnel. And you can see this material, this sugar cube structure within the face. You can have some mixed phase conditions, very fast changing conditions due to these fault zones. So let's see the different kinds of rock mass types we may find in this environment. Of course, we may have this simple bedded material, moderately disturbed, and we expect, of course, some wedge failures here. So if you see the blocky under small overburden, which is here under 150 meters, and high uniaxial compressive strength, so we have a projection of wedge failure. And of course, for an experienced tunnel engineering, this is straightforward. When we have a heavily folded formation of limestone here, you can see this is projected. This geosite chart, it comes from limestones and for alternations of limestones with other material that can have in these alpine chains. So here we have a foldy, highly disturbed, thin-bedded limestones with angular blocks formed by many intersecting discontinuity cells. And in this case, we may have some crown failures, chimney-type failures, and of course, some smaller wedge failures. We don't expect, though, large wedge failures because all these changing the scale, depending on the scale of our tunnel of this folding, can give you different scaling in your wedges. Another case is this brecciated rock mass. In this case, depending if it is you have clay infilling or not, you may have some severe raveling ground. So you see that here in this case we have a disintegrated structure, again under a small overburden and an overburden limit of 70 meters. We have raveling ground, and in this case you may have also experienced some settlement when you use heavy four-pole umbrella in order to face that. So you need to incorporate that also, and not put something heavy just to face this, to put some pre-excavate measures like light spiling. So you see here some photos of this raveling ground in the case, and of course in the portals you may face type H, the heavily broken disintegrated limestone with high clay presence. Here you may have some immediate dead load in your tunnel. So let's go then to put that in our tunnel. So we have to detect these different rock mass types along the tunnel, and below a bar with this kind of the prediction of the expected failure mechanism. So with these abbreviations, you see that wedge, chimney type, wedge, and raveling ground and chimney type failures. So let's proceed to the Flysch example. If you don't know about Flysch, Flysch is not a rock, it's a formation, and it's composed by rhythmic alternations of sandstone and peltic layers. You may have also some conglomerates, and it is associated with orogenesis, with mountain building, and it ends the cycle of sedimentation of a basin before the paroxysm folding process. By looking at this 3D conceptual model, and you can see this is just a fraction of a tunnel of 500 meters. These different sketches of phase mapping of, let's say, predicted phase geological rock mass types, you see different colors, and this is what prevails. If it's a gray, it's a siltstone, the weak material, and if it's orange, is the sandstone or a conglomerate, but mainly here is a sandstone, the competent material. And you can see also the folding, or if it's not very highly stratified. So in this case, we may have all these 6 different kind of rock mass types in this fraction of our tunnel, and depending of what prevails and how heterogeneous it is, this material, and how tectonized is this material, depending on the history coming from the mainly tectonism of this material. So our ground types here are complex because we have these alternations of competent and incompetent members. We have this profound bedding, and this profound bedding is continuous in depth. It is expressed due to this folding process. It's not sued in depth. So it's not a continuum mean in depth. So it is this joint like bedding, it is consistent in depth also. It is expressed there. And the bedding thickness variety from centimeters to meter scale also is encountered. And tectonic disturbance also transforms the initial structure and it can produce tectonic mixtures. On the other hand, we have also weak rock masses because we have the presence of clay formations, and we have degradation due to shearing and fissuring. So degradation doesn't come also to the structure, but also to the intact rock scale. And close to the surface, we may have severe weathering of the silty clay members due to the slaking processes. So these materials are highly susceptible to slaking. And of course, the groundwater here comes and downgrades the quality of the silty clay members and can produce high water pressures. And all these units are highly impermeable. Though you may have these sandstone layers due to the interlayers of the very impermeable clay stones or siltstones, it reduces rapidly its permeability. And this comes from the experience of many in situ permeability tests from boreholes within this material. So let's see this example. Here you see when we tunneled, this is one of the most expensive tunnels we had in Egnatia Highway, because though the overburden is not very high, it's up to 90 meters, this is up to a very big thrust. From one fleece, one geotectonic unit up on the other. So we have satellite shears, not just one tectonic zone and that's it. So it may have trapped big boulders of better quality rock masses like sandstone, but these are mainly floaters. It's like potatoes within this sheared rock mass, this sheared clay rock mass. So we mainly have a chaotic mixture of siltstone fleece in a geological environment. And you can say that when they have in some drawings from some boreholes they had, they tried to apply different geotechnical classification values, RMR, SKUs, GSI, by looking some boreholes. And maybe in your face, in the scale of your face, in your top heading, or also top heading and bends, you may find a better quality of sandstone, let's say, interlayer. And you say, okay, I have exited these tectonic zones and I'm entering a better quality. But this it's not continuum. So above that, it may have this sheared rock mass. So it cannot help, it cannot contribute to the overall stability. And that's why we have some severe strains in that tunnel. And many of designs and many support categories were applied in these tunnels. So it is not possible to detect specific zones of better or worse rock mass quality. It is better to apply in these small tunnels, let's say, a value for money, but also a continuum support category that can be applied in an optimum, let's say, support category can be applied in your situation. Of course, here a very worst quality rock mass. So from the experience of 12 tunnels in fleece environment, we derived in this revised GSI chart for fleece. And so these charts can help you just to classify your rock mass, describe your rock mass. And then if it behaves isotropically for your rock mass, for your tunnel, then you can use this value. So just to screen some photos here of sandstones and siltstones. So whatever prevails in the top lines, you have undisturbed rock masses. You can see these are certainty 11 rock mass types in fleece. So many types that can change from phase to phase within your tunnel. Type 3 moderately disturbed sandstones with thin films of interlayers of siltstones, and then the percentage changes, not here the tectonic disturbance, but just what prevails. And then we go lower in the lower floor when we have folded structures. Here, saltstone and siltstone interlayers in similar extents, but here the siltstone prevails again, but the tectonic intensity is the same. And we go to brecciated rock mass. In order to have a brecciated rock mass, you need a brittle material here. And in order to have a brittle material in the fleece, you need mainly sandstones or strong conglomerates or metasiltstones, which have a higher strength. And the tectonically deformed, intensively folded siltstone forming an almost chaotic structure. You can see here how the sandstone, let's say, tooth try to follow this plastic deformation. And here the blockiness is lost. We have a foliated structure, siltstone or clay shale formations with pockets of clays. Again, use it only for isotropic rock mass behavior. And of course, we can then get some numbers and quantify all this for the Flysch type, the geosize, the uniaxial compressive strength, the constant MI of the Brown, the deformation modulus of the intact rock, and then obtain from the rock data, from the rock science programs, the equivalent properties. Yeah, here just to emphasize that it is extremely difficult to take sample of an intact rock and representative specimen of a rock. So here, for very weak rock masses, we have a big uncertainty in the materials. And the knowledge are coming from back analysis of other projects of similar description of materials coming from that, because it's very, very difficult to prepare laboratory specimens for this kind of material. So I'm running out of time. Again, you can put that Flysch different. We will see their behavior, but I will cross two more environments and not be detailed about that. So you can see here a sandstone with some siltstone interlayers. It has some good stability because here it is horizontal. Flysch, it is folded, yes. It is inclined, yes. But in the scale of a tunnel, we can find them in the horizontal layers. So we may have some stable conditions or some wedge failures. When it is these are inclined, and depending on if it is towards our face or our tunnel periphery, then we may have some wedge consistent these kind of instabilities. And you can see some photos here of this material. When we have some severe foliation with steady inclination, then we're talking about some anisotropical failures here. So highly heterogeneous rock masses, and you can see here you need to analyze that in detail and provide different kind of parameters for the shear strength properties of the discontinuities, and maybe exclude the internal rock mass and discontinuity system and try to analyze that distinctly. And of course, when we have this severe squeezing ground and a chaotic structure, then we may have overall squeezing conditions around untunneling, not anisotropical deformation, but large deformation due to overstressing with the development of shear failures in an extended perimeter around the tunnel. So you can see for type 10 here, you can see the photo of the material and what kind of problems still yielding face our tunnels and shotcrete failures. And you can see what kind of overburden we may experience, few support problems, strain less than 1%, or severe squeezing or very severe squeezing. You can see the different depth we can face that just by first approach around our along our tunnel. I had an example of ophiolites here. I won't stay here because we don't have a lot of time, but I wanted to emphasize that the uncertainty that comes from this material is totally different. Here it is, of course, the environment that this is generated, but it's also the thrustic, tectonic thrust. It is connected with these ophiolitic complexes, but also to the serpentinization that can occur everywhere within the tunnel. It's not a surface problem, a weather alteration. It can happen during the crystallization of the magma. So we can find anywhere within our tunnel, not just on the surface. So you can see the uncertainty here. You may shift from this blocky rock mass to this heavily serpentinized rock mass to this highly sheared foliated rock mass. So again, complex rock masses, weak rock masses, from massive peridiotites, no serpentinization, very high in uniaxial compressive strength, then again very high uniaxial compressive strength, but reduced in strength along the shear surfaces, along the joints due to the serpentinization. also due to the intensity of the sedimentization, you may have reducing uniaxial compressive strength and the MI parameters, and of course the structure it being influenced. We can see that all this very nicely in the chart. You can see the arrow, the sedimentization intensity, how it can influence the structure. So we can shift from quality 1 to quality 2 and 3, and then have the heavily sheared brachiated rock mass due to the sedimentization. And you can understand again, structurally controlled failure, or in very large depths, brittle failures. We didn't meet any kind of these brittle failures in our tunnels. And then crown failures where sedimentization is intense. And when this is heavily sheared and foliated serpentinite, then we have squeezing ground. In molassic ground, we may have a similar environment like Flysch in alternate. The post-orogenetic nature of this environment, it gives them a totally different appreciation. So yes, we have heterogeneity, but only on surface. We have heterogeneity and heavily weathered rock masses due to the slaking processes. But in depth, all these materials are continuum, irrespectively, that doesn't have to do with what prevails, because all of these joints are shewed within the rock mass. They are not expressed. They are not, these rock masses are not folded, are not sheared by reverse folds. That's why we have very good rock masses in town. The only thing you have to be careful is in weathering in your portals, when your material, the same course here on the left and on the right, your material can be collapsed due to slaking after some months. You can see this picture. So very high geosize, and depending on the uniaxial compressive strength, we may have structurally controlled failure, or in depth some shear stress controlled failures due to the presence of siltstone. So yes, here in depth, we expect structurally controlled failure or stable tunnel sections. And when we are close to portals or close to faults, some faults, we may have chimney type failures. But close to the portals, we had some severe failures, circular failures due to this weathering, where we have some siltstones, highly weathered and very, very low uniaxial compressive strength, because the material is very recent, so the orogenesis is very low. And a very good job you can find in proceedings of WTC 2020. These are sentences highlighted in these different kinds of formations, and you can find the step-by-step procedure. So for all this environment, we can detect the rock mass types, and we can assign some parameters, but we will feel more comfortable if we put the rock mass behavior below with a distinct banner. And depending on either we have wedge failures, we can detect, of course, the principle of our support measures is to control, to keep confinement and restrict the relaxation, the disorganization of the rock mass. So retaining the discrete and stable blocks is our focus here, and the wedge analysis trace forward. There are certainly here is mainly has to do with scaling these wedges and finding the shear properties of this joint in order to calculate the factor of safety along your tunnel. So any certainty comes if we're not gonna scale, we're not gonna put the reality of the aperture, of spacing, sorry, of the consistency of the rock masses, of the discontinuity sets, sorry. So we calculate, we find our wedges, and then, of course, we had to find either by shear strength tests of natural joints. If we cannot do that, we can use here, for example, the Barton and Bandis and other more recent equations in order to calculate the shear strength properties of the joints. And here we can use the Smith hammer and the profilometer in order to assess the shear strength properties. Of course, then we can evaluate the factor of safety around the tunnel. And again, be careful to model the reality and scale the wedges. When we have a very straightforward wedge problem, then our support is mainly given in our anchors. The excavation step can be done according to not to disturb and not to provoke any, create any large wedges. So the rock bolt pattern strengthens the rock mass and keeps it confined and preventing possible gravity-driven failures, structurally controlled failures. When we have in portal areas and low overburden areas and fault zones, apart from the application of the salt screen and bolts, of course, we may have to put pre-support and spiling, or to use smaller excavation step in order to keep confinement and control wider gravity-driven failures. So we don't have to use heavy four-pole, just some pre-support elements of spiling. And here you can see in ground of limestones, heavily brecciated limestones, grouted spiles were used. You can see some concept of them that was applied in order to face these instabilities. And finally, when we have squeezing ground, we can choose either to have a rigid cell or a yielding philosophy in our tunnel. So I'm not gonna put my, of course, focus here, just to provide the focus depending on the failure mode. You can see here heavy cell or yielding over excavation of gaps in shotcrete and sliding steel sets can be used here if we have this kind of section in our tunnel. A typical support design for weak rock masses that was used in the Segnatia highways, you can see that in this section. This is a very generalized, but changing that in different kind of hebs, different kind of four poles or fiberglass. Of course, in temporary invert were used in order to face these phase control problems in the squeezing ground. So, ending my presentation, in order to go from the ground model to the ground behavior and the support principles, you see here that in between the link is a ground behavior assessment. So yes, in these columns we have our ground types, and we can assess all the key parameters. We can define either it is a rock mass or intact rock or the discontinuity properties. But then when we can assign different behavior types along our tunnels, and which kind of ground types we can, in which kind of combinations of these ground types we may have these behavior types should be assigned here in this kind of tables. And giving here the particularities, for example, which is the orientation of the main joint set? Does it play any role? The primary stress conditions, the groundwater, and then provide the rock mass behavior, not by just saying WG or CH, not by just abbreviation, but for your site-specific problem. And then your radial displacement or your phase stability, if you encounter or not. And then you can combine your rock mass with the behavior type and the support category type. And you can then proceed to the analysis, and either it is a numerical analysis, final element analysis, or unwedge analysis. So going to my conclusions, we can say that today's knowledge and the powerful tools we have in our arsenal have increased our capacity to design and construct more efficiently and in more and more difficult sites, and reduce the uncertainty and the acceptable remaining risk. But we are not at the end of this route. It is still always not possible to have an unquestionable answer to many of the problems associated with the work we're doing and reach the degree of accuracy that characterizes sectors of engineering. And this is due to many parameters. The spatial distribution of the geomaterials with uncertain or fuzzy margins, a dependency of the geological evolution, the big number of parameters with a broad dispersion of values, often for the same geomaterial, and difficult to test in sometimes. And the laws of behavior in sometimes still approximate. So the emphasis on the prediction of the tunnel behavior here and incorporation of the geotechnical designs and the assessment of the immediate support measures can reduce the uncertainty for the selection of the appropriate geotechnical analysis based on a more realistic geological model and failure mode, and the selection of more suitable geotechnical parameters for any analysis. And we can then narrow down any types of the support measures designed to control the evaluated failure mode. It is then obvious why the geological judgment for the understanding of the behavior must be always present and why it is so important. Before thanking you for your attention and for taking the full time of 1 hour, I would like to invite you to support the candidacy of the Greek Tunneling Society to host the World Tunneling Conference Congress in 2023 in Athens. Please visit the website of our candidacy. You can see many details about our program, and you can see just by the pictures that we Greeks, we design a lot of tunnels, different kind of tunnels, not only in the mainland but also in our islands, and we will be very happy to host you in Athens in 2023. Thank you very much. This is my last slide. And this is a field trip that is done every December in the Greek mountains by the program of the master program of the design and construction of underground works, a specific programs for tunneling of the National Technical University of Athens, of the mining engineering department and the civil engineering department, and here, of course, by the engineering geological masters for the university. I am now a professor, and we have also we are very happy to have year by year postgraduate students also by the Geoengineering Center of the Queen's University in Canada. So thank you very much for your attention. You can see here some faces you know, and they host right now this British tunneling workshop, this webinar. They are already young tunneling engineers, and we are very proud of them. Thank you very much for your attention. And this to run also the reference that you can find the material for my presentation. Thank you very much.
So thank you very much, Dr. Marinos, for this brilliant presentation. Quite interesting material there, quite accurate. My name is George Dulkas. I'm a member of the BTS Young Members, and with coordination with the Greek Tunneling Society Young Members, we organizing this workshop. So a big thanks to everybody who is attending today with us. May I propose that we use the chat tool to type in any questions we might have from this first part of the workshop while we start moving on to the second part with Dr. Andreas Benardos. Thank you very much.
So just a second. Thank you for your patience. And George, can we have it in the first slide, please?
Yes, let me try once more.
So, hello from me and good afternoon. It is my great honor and privilege to make this presentation, and I must thank the organizer for the kind invitation, and I hope that in the near future we'll having the opportunity to have such meetings in real person. Until then, the technology is providing us the means to bypass these obstacles. So, without any further delay, I should start with my presentation. And of course, in the title, you can see the words uncertainty and cost as the major keywords that appear. And in my mind, these two issues require a more rigorous tackling from the tunneling community. Thus, we should first try and understand them, and then we should devise tools and methods to manage them. Professor Marinos made an excellent presentation regarding the characterization of geological and geotechnical properties and uncertainty of the ground medium. This is the fundamental info that we need to gather so as to have a successful implementation of the underground project. In this presentation, I will try to cover such approaches and present some cases that I hope that you find interesting. So the first part is dealing with the uncertainty, and the second part is having some insights about the linkage and correlation between the condition encountered and the construction cost. But let's start from the beginning. We are dealing with the special construction type that encompasses development of engineering structures below ground surface. This alone involves a lot of ingenuity, a lot of novelty in technology, and of course, a lot of decisions that are to be taken on engineering judgment. And of course, the intuition of the responsible persons. Thus, it is not far away from being an art, and in these books, you can see that this is further strengthened. Who gives his definition of the art of tunneling, saying that the art of tunneling is the recognition of the most probable failure modes for the rock conditions and the selection of the appropriate excavation sequence support methods to maintain the tunnel profile. And of course, the rock conditions are the ones that we should focus and find the most compatible and cost-effective designs for them. Actually, we're now in the more need of this art than ever before. Underground construction and space development has begun a great part of the construction industry. This chart expresses just that. You can see the evolution of metros and witness the surge in the development of the metro systems in the past 2 decades. Actually, we are now commissioning new metro lines at a pace of approximately 1,000 kilometers per year. And this growth is expected to continue in the future as more and more urban space become overcrowded. Nevertheless, apart from the metro, we are now engaging in the development of more coupling designs to place in subsurface environments all infrastructure and facilities that are not needed or unwanted on the surface, or to relocate underground the ones that can perform better in such environments. In these pictures, you can see only some of the new exotic spaces, from physics labs to sewage treatment plants to oil storage facilities that are so needed in modern societies. So in this context, underground development is here to stay. Underground space development provides an extraordinary opportunity to have the job done efficiently and, more importantly, with a great environmental sensitivity. This can counterbalance the fact that underground projects are, in general, more expensive in capital expenditure than the respective surface installations. However, what is greatly accepted is that there is always the risk of having great overruns in terms of cost and scheduling delays. This element still exists, even though great efforts are made to minimize these mishaps. Here are some examples of notable failures in the development of tunneling projects, especially in urban areas where in the majority of the case, adverse ground conditions exist, and also the threat to third parties is significant. The first example is from Germany, during the construction of the Munich metro, where a major collapse was taking place. I think that you all recognize this one. This is from UK, during the construction of the new, at the time, Heathrow Express tunnel, and you can see the severe impacts to the existing surface buildings there. Moving on, we are now in Athens from the construction of the Athens metro in 1998. The tunneling activities had a number of problems there, and in the picture, you can see the aftermath of a major chimney collapse that occurred on live TV, where a kiosk had been literally swollen by the void that was created. The next is from China, from the construction of the Shanghai metro. You can see the result of the extensive surface settlements that occurred there. Once again, from Singapore, this is the MTR line, in this incident, this is called the Nickel Highway collapse. You can see again the consequence in the near field. Next one is from Cologne Metro, and you can see some devastating pictures. And the last one And the most recent one is from in China, in Xiamen Metro in 2019, and you can see also the surface effect of this collapse. The previous images can give an idea of the magnitude of the problems. The Hong Kong Civil Engineering and Development Department has actually issued a very interesting publication, which is called Catalogue of Notable Tunnel Failures and Case Histories, and in there, some details and mechanisms of major tunnel collapse are presented. Of course, besides the negative image and publicity of the failures, there's also some tangible aspects in which you can see in this list. This list was issued by Munich Re and was published in 2011, linking and describing what's happening in terms of failure in the last 20 years in tunnel projects. This report indicates that recovery costs were really heavy, and perhaps insured was being considered the cheapest risk management tool. You can see that the total cost and the total claims is in the order of 1.2 billion US, and actually the delays are also stunning, reaching up to almost a combined total of 20 years. If one also takes into consideration the loss of income due to the delays, then the total cost of this failure can reach a few times this figure. All the above has led to the development that Vasilis also told his presentation, a very grotesque actually saying that a tunnel is a hole in the ground with an engineer on one end, a lawyer on the other, and the constructor's truck in the middle. The uncertainty of the properties of the underground medium influences the development of this underground project itself. And by saying that, I must remind you the most recent definition of risk from ISO, that is that risk is the effect of uncertainty on the objectives. So in this context, uncertainty can give rise to risk conditions that they can yield increased project cost. What should be done is to find measures and techniques to manage and control this uncertainty. And of course, in this slide, you can see some, let's say, the framework of the whole uncertainty in the underground medium. In doing so, we need to first understand it. Many researchers are dealing with it, and in this slide, you can see a basic discrimination of the uncertainty, the aleatory and epistemic one. The aleatory uncertainty is related to statistical difference in measurement of values, either from measurement devices or in the natural randomness of the property, and the episystemic one is related to the systematic results, the measurements, to modeling errors or gapping our knowledge. Besides the above theoretic framework of uncertainty, I try to be more practical and include the reasons of having the uncertainty. This is you can see the variability of the property values in the inherent randomness of the ground medium, the statistical variation of the measurements, the subjective judgment disagreement. For example, what is the GSI and RMR values? Some linguistic imprecisions, for example, the rock mass is good or the rock mass is bad, or, of course, approximation errors that arise from our usage of simple or oversimplistic models to assess the behavior of complex systems as the ones governing the ground response to excavation. The real issue is that we are sometimes unable to accurately define the ground condition, as unlike any engineering material, we don't have exact or accurate values that can characterize it. More importantly, though, if we manage to get some values, we're not actually certain if these are representative of the entire volume of the ground medium. The complexity of geological conditions with respect to these types can be found in this table 1 by Venturini. And of course, moving on from sedimentary to metamorphic rocks, and from simple tectonic events to a more rich tectonic history, complexity and uncertainty about the actual conditions increase. All these give rise to clauses that like differing or unforeseen ground conditions that can yield claims and dispute between the involved parties. And if newer types of contractual conditions exist, for example, the geotechnical baseline report, uncertainty still dictates a great extent of the most evolution of the underground project. So the question that really arises is the one, how to take decision under uncertainty, and of course, how certain or how uncertain are we about the prevailing uncertainty level of the ground conditions. In pursuit to manage and control uncertainty, this slide presents some options that we have. Of course, the first is obvious, conduct a more ambitious investigation campaign. And of course, this is the best way of us getting coherent data. And of course, this is the most expensive one. The two other methods actually can be used to devise data and fill in the space between boreholes and point samples with new interpolated data. Probabilistic modeling approaches can be used to incorporate knowledge of the distribution density functions of a range of values, and spatial analysis can be used to extend our knowledge and interpolate new values in areas where actually no data exist. Let's start from the first. In this slide, you can see through the investigation campaigns, point sampling is our principal way of knowing the properties. However, samples are just a fraction of the construction volume, and actually their volume in relation to the whole excavation volume rarely exceeds 0.0005%. So, as you can see in Carter's diagram, there's a direct negative correlation between uncertainty and risk with the intensity of the geotechnical investigation campaign. This is something that we can further see in this slide. These diagrams are from a study undertaken in the US, covering about 84 as-built projects. The first one reveals the percentage of claims with respect to the ratio of the total length of investigation boreholes to the length of the tunnel project itself. So if this ratio exceeds the value of 1.5 to 2, then the claims can be significantly controlled. The second diagram presents also the same. If the cost investigation exceeds the threshold of approximately 3% with respect to the construction cost, then the project as built cost is in line with the initial cost estimates. Passing on to the probabilistic modeling, I have a personal favored example that I'm going to show you. Actually, it is found in the book Supported Underground Excavation in Hard Rock, and it was one of my very first experiences with this type of uncertainty. You can see the guys on top, and you can see that the dilemma these guys are facing that actually presents two extremities of a risk-averse and a risk-taking attitude. Of course, the truth is somewhere in the middle, and if we can take, for example, a simple bolt design exercise that was mentioned before, we need to know first the bearing capacity of the rock bolt and the weight of the roof slab. The ratio between these two is the factor of safety, and you can see how it is calculated in the top corner. So, if we do a simple deterministic assessment, when we have a safety factor of 1.3, and we're very happy with it. The real issue is if we actually, this is the case, if we have this 1.3 as a safety factor. And in the stochastic approach I'm going to show you, we don't only take into account the mean values, but we incorporate the whole range of probable values as given the probability density factors you can see on the bottom of the page. The first variable, of course, to consider is the thickness of the slab, which, as you know, varies from place to place. And the second variable to be modeled is the rock bolt's capacity as derived for a series of pull-out tests. So, with no further delay, let's pass on this, let's say, assessment in which you can see the modeling being made by the Monte Carlo simulation. We are running this simulation for around 1,000 iterations, and each new iteration actually depicts the realization of a probable scenario. The more the better, and as we progress, we find that we are getting results of a safety factor and guesses as another probability density function. This time, however, we can quantify the uncertainty and we can have a full control of the issue. We can see in the chart that we have an 80% chance that our safety factor is between the value of 1.1. So now we have, instead of having this fixed deterministic answer, we can now have a more great control in the uncertainty of this on this issue, and of course we can take decisions with that. Sorry. So, previously I talked about spatial modeling. This is what I'm going to talk now. My background is mining engineer, and in our attempt to find all distributions, we're usually employing spatial modeling techniques as the first things to do. Likewise, these tools that are made available this time have been evolved and now can be further used to model and describe not only the ore grades that we use to search, but also lithological types and geotechnical properties, as the two examples you can see in the slide. The main purpose is to interpolate values and pass from pre-knowledge to a 3D grid that can have values filled in, bridging our gaps in space and in our knowledge. Through this, we can certainly get insight into what's actually going on underground. The first case I'm going to speak about I'm going to present what exactly deals with this spatial analysis. Is from Greece and is related to the ground conditions encountered during the construction of the Lavrion Technological and Cultural Park and the underground hazardous waste at the site. This is part of the remediation activities that took place there, and it was decided, instead of having the waste packed and shipped to a German underground repository, to build our own repository on the site. In the slide, you can see on the left the layout of the repository, the access tunnel, and the main area, which is developed following the principles of room and pillar mining method. The facility is constructed within the upper marble geological unit, just below a strata of impermeable but of low quality tectonic nape that is comprised of fillets, schists, and graphic schists. In this slide, you can see also the 8 boreholes that was made during the investigation period. And actually, we have 8 boreholes approximately at a distance of 30 to 50 meters apart one from the other, in order to fully decode the geological setting and pinpoint the construction site, as we needed a good layer of marble to place our design. However, at the end of the access tunnel, at first we witnessed some overbreaks, and finally the intrusion of strata of graphic schist was revealed at the roof at the levels ranging approximately from 16 to 17 meters. Governing the crown, as you can see on this face mapping, you can see on the right. And some local collapse you can see, but this is not so interesting. The problem actually raised a concern of the stability of the pillars, not of the tunnel roof itself, but of the pillars were the major concern. It was, as the days go by, we became more sure that was a rather local feature, that was accented only in the central area, and it was decided to tackle it with a more aggressive support measure. So the construction continued, and we had able to pass through the zone. However, it was stunning for us to see that in these 30 meters boreholes under all this investigation, that we weren't able to pick up what's going on underground. So we tried to make an assessment of if we could be able to pinpoint this anomaly from the early stage of the phase of the initial investigation campaign using the actual initial borehole data. The answer was to, of course, take all this data and develop models to capture the spatial behavior and distribution of the ground geotechnical conditions. We did thus with SURPAC. SURPAC is a mining software, and we developed the 3-dimensional block models in which you see. Of course, this is not as easy as it looks, and the goal is to achieve a required accuracy, so I'll develop a valid block model, one that can rely on. A total of 132 samples from UCS and was taken into account, along with samples from RQD that from the boreholes, and we were able to produce the block models that you can see. I'm not going into details about model generation, and instead I'm going to focus on the results attained and their interpretation. In the slide, you can see the total block models of the area of investigation, which ranges from the level of around 10 meters to the level of plus 25. Through them, we get some quantitative analysis and information, and we were able to compare the model with the actual conditions and, of course, to identify the risk-prone areas. Let's see in detail the results of the UCS modeling. In the upper picture, you can see the blocks having values between 20 and 40 MPa, representing the graphic schist strata. You can see that this lower strength unit is deepening at the eastern part of the complex, near the entrance area. This can also be seen in the sections where the UCS values are shown from top to bottom, from the levels of from 19.5 meters to 12.5 meters. In there, you can see more clearly the graphic schist in the entrance, reaching close to the complex roof in the elevation of 17.5 meters. However, another weak zone is revealed at the western part of the complex, below the level of 12.5 meter, which of course is not an intrusion of the graphic schist, but actually a lower quality marble formation. Here we have some 4 sections, also focusing in this area. You can see that sections 1 and 2 reveal a low strength area, approximately from the levels above 16 meters, and also the low strength area at the central part of the complex below the level of 12 meters. There is some modeling from the RQD values, and the result telling us also telling us most or less the same things. The most intense fracturing is found in the area of the eastern border of the facility, especially at its southeastern corner. Also, it was found that in the eastern part of the roof section, the RQD values are almost 10 to 15% lower with respect to the values estimated at the central part of the facility. Now, we have the option of seeing what's happening in the rock pillars, and this was a great insight for us. And we can see in this slide both the graphical views and the quantitative statistics and distributions that we have obtained. In the picture, you can see the UCS values in the upper picture, and in the table, you can see the detailed analysis for the values derived from each one of the pillars in the facility. So we have information about the load-bearing capacity of any individual pillar alone. It seems that the UCS values of the pillar is quite high, and they are not actually affected by the weak zones. Pillar number 5 has the lowest strength, especially due to its low strength zone in its base, while pillars 8, 9, and 10, which actually is a concern for us, showed pretty good strength values. In terms of RQD, we can see that, of course, these two pillars 9 and 10 are more affected by the graphic schist intrusion, but their values remain at acceptable limits. So we have the opportunity to have an overall picture of what's going on, and we have discerned the facility in 3 sections, E1, E2, and E3. And what we can see is that E1 seems to cope very well without any really problem, and E2 seems to be E3, sorry, seems to be the most vulnerable of all. So this is a fairly easy analysis and easy application of the spatial distribution in order to get insight of what's really happening underground. And now we're going to see another example from the Athens Metro case, where a more complex spatial analysis and probabilistic modeling has been made. Of course, as you understand, the metro construction and urban tunneling in general has to cope with a number of challenges that result from the complexity, the heterogeneity of the formations, and from the presence of water that increase weathering, and of course from all man-made structures that influence the tunneling zone. Furthermore, the use of TBMs is used in the majority of cases, and this further makes them more susceptible to problems, especially if conditions of great variance are encountered. As TBMs are tailor-made to cope with a specific set of conditions with ease, this feature is actually the Achilles heel, as they have difficulties when encountering conditions outside their working envelope. And to this end, spatial analysis is a plus to our knowledge, as the one you can see in the figure from the research of Stavropoulou, where advanced kriging algorithms are used to identify the geotechnical properties and also conduct advanced 3D geometries to be used in subsequent numerical analysis studies. However, if we don't have sufficient data, then the uncertainty level of the interpolation can be very, very difficult to achieve. So in this situation, we must resort to a more complex type of analysis and use correlation between known data and unknown data so as to establish some guidance of what to expect. Going to present you the case of Athens Metro, and in this case, actually, we're going to deal with the analysis of an interchange in the Katehaki Panormus section. It was part of the line 3 of the Athens metro construction, and is actually one of the largest interchanges with almost 1.1 kilometers in length. In the picture, you can see the tunnel running under the city, and of course, the boreholes that were available in the investigation. In general, the problems in the constructions of the Athens metro, apart from the man-made structures, were the heterogeneity and the reduced strength of geological formation, the extensive fracturing, and of course the weathering. All the above have created some major problems related to the phase instabilities, surface settlements, and weather inflows that made it very difficult for the TBM to pass through. In the model I'm going to present, we have used a number of 8 parameters relating to the prevailing condition, and these are the fracture degree as represented by RQD, the weathering degree, and all the others you can see in the slide. And each one of them actually corresponds to a behavior type that can affect tunneling. For example, the most important parameter designing the TBM is the UCS. And of course, the RMR classification used to describe the stand-up time on the excavation or the overload factor can assess phase stability. On the other hand, the selected method of tunneling has its own qualities and characteristics and its own needs. In this matter, the thinking is that once we establish an assessment of the compatibility between the construction method and the actual geotechnical setting, we can then easily obtain data on how well we can know if we have a good situation for tunneling or a bad situation for the tunneling process. The data that we have come from a number of 16 boreholes, and that actually identified almost 36 lithological types. In the 2 borehole logs on the left, you can see these data types that we had. This is lithology, RQD, MR. MR is actually an RMR derivative, especially designed to cater for poor ground conditions that Athens Metro design team used, weathering degree, and also some laboratory tests at specific points. In order to proceed with the analysis, we have first tried to reduce these 35 lithological formations to 8 main geological units, which is breccia, sandstone, siltstone, limestone, silts and shales, alluvial, conglomerated materials of fracturing zone. Also, in this slide, you can also see on the light orange color the 11 areas that were used for the analysis. These are the 11 segments, each one of them covering an area of 100 by 100 meters following the TBM's path. Besides this horizontal division, we have also divided the tunneling path vertically in 3 layers, each one of them being 4 meters thick, so it was to cover 12 meter thickness, covering the 8.5 meters diameter of the tunnel diameter. Of course, the next thing to do is to rate the parameters accordingly in order to be able to capture their influence to the tunneling process. In order to do so, we have selected an interval classification type, taking values from 0 to 3, from the worst to the best condition. That denotes that for 0 is an adverse condition to cope with, and 3 is a very favorable one. And of course, these ratings are adjusted to take into account the construction process, in our case, the double silt TBM. If a different construction approach was to be used, then of course we need to adjust of these ratings to cater for the characteristics and the individual qualities of the construction method. And furthermore, in order to be able to enhance the resolution of the analysis in poorer conditions, special focus was given on the lower values of the classes. For example, you can see in the RQD, this is in the upper left corner, you can see that special emphasis is paid to values lower than 60. So analysis is the next step to do, and the 3-dimensional spatial analysis is being done by GIS software using Kriging algorithm or inverse distance weighted methods directly using the borehole data. In this step, the values obtained from the spatial modeling are extracted and form a distribution function of the model parameter itself, which actually mimics the behavior of the parameter. Through the probabilistic modeling, these probability distributions are then regenerated to depict this time the class values, and using the discrete probability by employing these threshold values that we saw earlier in the rating, then we have a kind of information about what class to expect and what is the probability of occurrence. For example, in the slide, you can see that we have a probability of occurrence, the class of 0. This is very adverse conditions, the order of 20%. We have probability of occurrence of the class 1 for approximately 40%, the class 2 approximately 30%, and the class 3, which class 3 is the most advantageous one, are approximately 10%. So in this manner, we can have all the spatial data being constructed to ratings that are going to help us make the whole assessment. But of course, we don't only have these types of analysis. We have, of course, this type of analysis in areas we have a lot of data to gather and process, RQD, MR, the river burden, the hydraulic head, as you saw. Of course, we have some other data that are not so abundant. So it is not a wise thing to have this as a spatial analysis, because it is not adequate enough to have an analysis of being extremely helpful. It's going to be an erroneous analysis. So what we need to do, we need to correlate this data with some geological units. So in doing that, we first perform the spatial modeling of the geological units and then interlinked their properties to them. So the first spatial modeling was made in a kriging type, an indicator kriging type, using 1 if we had this geological unit present, 0 if we didn't have it present, and then we multiplied the probability of having the geological unit along with the actual property of the respective property of this continuum. For example, sandstone's probability of occurrence with the sandstone permeability values. And but how do we know this type of things? Because we don't have much. So what we did is we used all the data from primary sources. Of course, they were limited, as I said, but of course we had some secondary data that we could use. So some secondary data were data from neighboring areas, or even engineering judgment, or in the absence of all these, maybe bibliographical references. In this slide, you can see just that. On the left, you can see the spatial modeling of the geological units, and in the left, you can see the related data coming from probabilistic analysis that we used to make from the UCS values. So by making this fusion, we devise new data using the probabilistic modeling, and we end up having the rating of the geological linked properties as discrete probability functions. So we now have a whole range of data to process, and in the next slide, you can see just about that. These are the ratings we had for each segment, and for each parameter. So this can give us a brief idea of what to expect. For example, for the compressive strength of the formation that is on the bottom left corner, we can see that the first two segments are characterized by rather adverse conditions, having values of 0 with a probability of occurrence around 40%, while the most favorable condition could be found on segment 5. However, even at this stage, it's really difficult to make a coherence assessment about the best and the worst areas that we can come up. To this end, a weighting of these parameters could be most appropriate in order to have a unique value that can characterize the vulnerability. In our case, we have used the rock engineering system principles as given by Hudson, and the interactivity of the parameters is the indicator of the importance of the system, and so the method has been selected to do so. And of course, someone else could use some other multi-criteria analysis, such analytic hierarchy process, to prioritize the parameters. Here you can see the matrix that was developed and the ESQ empirical semi-quantitative rating that was applied to come up with the results given in the table. And you can see that 4 are the more dominant parameters: the fracturing degree, weathering, Rossman's rating, and hydrological conditions. final vulnerability index is given in this slide, where the rating of each parameter is multiplied by the weighting of the respective parameter at a scale from 0 to 100, with 100 being the most adverse and most vulnerable condition. You can see that the best conditions are found in segment number 7, which has a central value of around 40 and an upper limit value of around 60. Accordingly, we can see that the segments presenting the greatest vulnerability are segments 1 and 2, having central values around 60 and upper values of around 70. So the validation could be made directly by looking at the problems encountered, but in this slide we can also see an indirect validation way using the achieved advance rate of the TBM, that is excluding all delays caused by external factors, mechanical failures, etc. The first graph actually gives this vulnerability index with respect to the TBM's advance rate, and you can clearly see the development of 3 clusters of segments: the best, the medium, and the worst area. You can see segment 7, the best, segments 11, 6, 8, 9, 5, and 6. This is the central part of the segment, and we have also 4 other segments being the most vulnerable ones and having a correlation of minus 0.9 for these 2 variables. In the second graph, you can see the cumulative tunneling process for each segment, and we can again see that the TBM drives the 100-meter tunnel in approximately 7 days in the case of segment 7, which is the best, and it needs around 26 days to cover the same distance of segment 1. What we can further see is that although we had classified segment 4 in a lower vulnerability state, it exhibits almost the same behavior as segments 1 and segments 2. As we have looked into it, we have found that there's actually some significant delays. You can see a plateau in the process, and but these delays were from a collapse that was caused by the encounter of an old well in the tunnel. Final assessment of the vulnerability index, you can see it in this slide, and you can see also here the 4 major categories that we had in our case. This concludes the first part of the uncertainty, and now we can advance to the part where the money is, the construction cost. In this section, I'm going to present some work made by me and Dr. Chrysosthemis Paraskevopoulou relating the cost of Greek tunnels. I should not go into any details stressing out the importance of construction cost, and so the first thing anyone asks you is how much does it cost to build a tunnel, followed by some other questions like what is the cost performance of the project, or can you do it with less money that the others are doing it, or are the others doing it with less than you? So we need to first come up with some efficient tools that will allow us to accurately assess the cost of underground project. And this is a long-standing requirement of all the involved stakeholders, as they need to have more insight in the process of making decisions about the project. Secondly, in our competitive work, we need to use the benchmarking as an essential method of comparing performance, and we must try and compare costs from similar projects. But more importantly, we need to identify best practices so to be benefited from their use. In order to know the main cost drivers of tunnel construction, the following parameters are given. As it is obvious, there are many parameters as given in the slide, for example, the purpose, the length, the size of the tunnel, geotechnical condition, the standards applied, etc. Worldwide research was conducted to tunnel stakeholders, constructors, designers, concluded that the main cost driver, of course, it's not something we didn't know, are the encountered geological conditions followed by the applied construction type, thus meeting the requirement of these conditions by designing compatible methods of excavation and support, as Hook proposed, can influence our ability to control cost. Let's move to the breakdown of the tunnel construction cost, identify what are its main components. These are the 2 notable research I'm going to show you. The first is from Greece, covering almost 100 kilometers of tunnels constructing the Egnatia Highway. And it is shown that approximately 65% of the cost is relating to the excavation and preliminary support. The second comes from Efron and Reed, that covers a wide variety of tunnel cases worldwide, And in there, the excavation cost ranges from 60 to 70% of the total construction costs. These two research coincide, and thus we can deduce that the excavation support is the major component of the cost, almost 70% of the total. In order to have a cost assessment of the Greek tunnels, we need to have always accurate and reliable data. This is an important requirement. In our pursuit, we have analyzed the construction cost of 9 transportation tunnels, having a total length of 16 kilometers. And in the map, you can see that they were constructed in various places in Greece during the last decade with the most up-to-date standards and cover a wide spectrum of geotechnical conditions. And of course, we have at our disposal cost data coming from mainly the as-built reports. What we aimed to do was to get insights regarding the construction costs and to try to correlate and link it with the encountered geotechnical conditions. The methodology that was used is based on the principles of case-based reasoning, and this method uses the past experience or knowledge gained in order to make assumptions or propose choices to be applied to new situations of future projects. In this manner, we have analyzed the tunnel projects thoroughly in an attempt to extract cost data coming from each type of design, cross-section that correspond to certain geotechnical conditions. And in doing so, we have found some linkage and cost range estimations between them and the GSI of the encountered conditions. Of course, this is not an easy task, and by just throwing and gathering numbers, it's not something that we cannot work. As you can see in this table, by just having the final cost of the tunnel, you cannot do much with it. You can say, for example, that the average cost is the order of 10,000 euros per meter, but actually the variance is too great. It's from 2,500 to 25,000 euros per meter. So it's something that we can't just use without any caution. So we need to be really meticulously with the handling of the data. So we need to register all the excavations and support measures adopted, all the resources, and recalculate all the cost using the unit pricing method and the required materials and resources. Here are the results obtained from the data, and you can see on the table some 5 rock mass classes that was used in the analysis from A to E. A is the best, E is the worst, and of course the median cost per cubic meter that each of these categories had. In the chart, you can see also these categories along with more details as the mean and max values, also with lower and upper quartile values, and of course the median as also shown in the table. As you can see that moving from good geotechnical conditions to really challenging ones, the cost also escalates. We can see that category A has very little data, and this is also resulting to have less variances in its figures. The greater variance is experienced in category C, where we have a median value of 90 euros per cubic meters, and almost 50% of all cost value lie within a range between 60 and 120 euros. In any case, these figures show a strong relation between cost and conditions and encountered, and can be used as a first-order assessment of the expected cost of the tunnel project if we can really identify correctly the encountered conditions on the construction site. Let's look more close. Category C. This is the category with the most variance, and we have data coming from an application length from approximately 4 kilometers, coming from 7 tunnels. And if we focus on the cost per cubic meter, we can see the variations from first hand, and this might be explained by the extreme sensitivity of the construction to the geological conditions, or even to the different approaches that the designers employ to bypass this poor rock mass. It might also indicate that perhaps our GSI class from 15 to 35 is just too wide, and it needs some refinement to actually capture the trends. Here are some correlations between GSI and the cost of either in terms of cubic meter of tunnel or meter per cost per meter of tunnel constructed, which can be also used as the quick assessment tool. And of course, Here are some another correlations that we had between GSI and cost per meter of tunnel when also incorporating the span of the tunnel in the analysis. So, leaving all this, I must go to the benchmarking, and there are some slides on that. We just inspired that benchmarking, having read an old report from HM Treasury that actually wanted to evaluate the construction cost of tunnels in UK as related to the ones of continental Europe. I haven't made any changes to the actual data. I have simply injected the Greek data in this figure. So UK data are the maroon dots, EU tunnel data are the red diamonds, and the Greek tunnel data are the blue triangles. This is cost per kilometer in British pounds with relation to the tunnel's outer diameter. As a general trend, we can see the positive correlation between the span of the tunnel and cost. That means that the increase of the tunnel, of the span of the tunnel, results to greater construction cost, which is also something we expected. Greek tunnels, of course, are more concentrated between a diameter between 10 and 12 meter, while data coming from EU and UK data are covering a more wide range of values. This figure is linking also cost per kilometer with the length of the tunnel project. Again, we can see a small trend is forming, indicating that longer tunnels require less cost per kilometer, and this is especially shown for the cases of the UK tunnels. For the Greek cases, the data are not sufficient enough to make such a definite assumption, but we can assess that their cost is lower than the EU and UK cases, around £15 million per kilometer, where the UK tunnels are in the cost of about 15 to 20 million pounds per kilometer, and the tunnels in the EU is around 25 million pounds per kilometer. That concludes my presentation. I think that I have bombarded you with enough data and concepts already, and I think that everyone could have its own conclusions about uncertainty and cost. And of course, we should try and increase our accuracy in assessing both issues, as this will end up improving the way we make safe and cost-efficient underground structures. Once more, I would like to thank the organizer for the kind invitation. And as Vasilis also told you, I hope that you can be our ambassadors for the Athens candidacy for the WTC conference of 2023. We hope with your help, we will unite the technical and scientific world in Athens to discuss issues and to promote the expansion of underground engineering. So hopefully we will have the opportunity to meet all together in Athens in May 2023. Thank you for your attention.
Thank you, Dr. Benardos, for your delightful presentation. I think you did say you bombarded us, but I would say that it's always a pleasure to be bombarded with such valuable information. So I think on that note, we'll start the Q&A. I think we had a few questions for Dr. Marinos from Asil and Thomas. So if Asil and Thomas, you're still on the line, should we start with Asil's question first?
Sure. So I have replied to part of it. The first question was why does initial stress ratio has low sensitivity of Rockwood's factor of safety in terms of the block theory of failure? And my understanding is it has a significant sensitivity, because if you use the in situ stress ratio, then the factor of safety is increased. Then follow up is that I tried testing this sensitivity through an unweighted numerical model to check the sensitivity of initial stress ratio in structurally controlled failures. Can you suggest how to refine my approach? I have to say that I haven't studied that in detail in order to see that, how this can be refined in an unweighted program. But I would say one of my suggestions was to see, depending on the scale of the wedge, to see how this it is affected. So to change the consistency, the discontinuities, distance, and the depth of consistency of these joints, and to scale the wedges in order to see how these are affected. And the other one, of course, is the opening.
Okay, I believe, are there any further comments on that, Asil?
Thank you, Dr. Marinos, for answering the question. I'll apply the parameters that you mentioned over there and come back to you if it's okay with you with the results.
All right, and then we had a question from Thomas, which I think you replied as well.
Yes. Yeah, this is a straight, a usual question, but very, very interesting. But what are the merits of conducting a sensitivity analysis as regards the rock mass properties instead of allocation of a single value for each parameter in order to address the uncertainties around the ground perimeters and their potential impact on the behavior of the tunnel? And my reply was that when your index rock parameters like the UCS, like the MI, or the modulus ratio, the deformation modulus of the index rock, when these range considerably, mostly that, and the rock mass classification value, then you can study, and it provides an understanding of the lower and upper bound level of your support requirements. So depending on that, you can see the intensity, the severity of your stress-induced phenomena around your tunnel, or either it is squeezing or rock burst phenomena.
Of course, thanks for your response to that one as well. I would now request the attendees if they can raise any further questions they have, or click the raise your hand icon to show if that they've got questions. Whilst being mindful that we've got probably another 10 minutes remaining. I think there's another one from Asil here. Asil, would you like to share it using a voice link?
Surely. Good evening. My question for this is regarding the uncertainties of the cost analysis of tunnels per unit length, as was shown in the second presentation. And what I've read previous papers in which they show that the cost of the tunnels changes exponentially with the diameter from previous papers. But here you analyzed using the per unit length of the tunnel. So can you shed more light on that? What would be the effect of the diameter of the tunnel on the cost?
Thank you for your question. Of course, you are actually right. When we tend to increase the diameter of the tunnel, the cost can increase exponentially. This is because from when we move on from a 12 meter diameter to a 14 meter diameter, this 2 meter change the whole structure of the design, and of course yields greater impacts in terms of excavation and the actual support costs. In my mind, I don't want to use the construction per meter length of the tunnel, because it is actually not a good indicator. It's a good indicator only if you have this certain type of the same diameter in tunnels. In our case, in Greece, we used some tunnels that had more or less the same characteristics, so we could use it. If we are going to use this index in other tunnels that are very, very different characteristics, then I would suggest that you should use the cost per cubic meter of excavation. This is a more safe, let's say, index But of course, we also need into account the individual characteristics from each data. Relating to this question, I haven't used any, perhaps you are referring to the last two slides that I have showed. This is from Her Majesty Treasury report. I don't have the exact data. I just used these tables and then injected my own data in it. So I don't quite know what's happening in UK and in EU tunnels. I know what's happening in Greece in the tunnels that we have designed. They are more or less around 100 square meters of diameter, from 10 to 12 meters diameters. And then, yes, in that application, we can use the meter, the construction, the cost per construction of meter tunnel.
All right, thank you.
So have you got any other questions on the line? Okay, we've just got a question that's come in. Would you like to unmute and share it with others? Oh, sorry, my bad. It's just a thank you note. I think if there aren't any questions, and being mindful that
I have a question.
Oh, okay.
I'm sorry for not being able to post it on the chat. I don't know why it's not. It doesn't work for me, and I've also been raising my hand, but that doesn't seem to work either. So I have a question for Dr. Marinos. The failure types that you have specified and elaborated on are based on data from 62 tunnels of Egnatiados. And indeed, the geological environment was quite varied. And to be more exact, it contained practically all of Greece's geotechnical zones. So this is really valuable information. On the other hand, the method used for all the excavation of all these tunnels was always, or maybe almost always, in a two-phase conventional method. So this is my question. Had the excavation been performed in a non-conventional method, by TBM, for example, would you expect to come up with the same, more, less, or maybe different failure types?
Thank you for your question. This is something that I'm sure that that also works in TBM method, because the philosophy is the same. Now, of course, cannot be exactly the same, and it cannot, let's say, direct with the same focus on the support principles, but to the selection of the appropriate TBM machine. So either we shift from a rock TBM to a silt TBM, to a double silt TBM, or to a phase support requirement, either by the slurry or earth pressure balance machines. It surely can be dictated by the failure modes. So I would say that this is definitely work we have been working on. However, this is narrowed down to less to more specified geological environment, the data we have, and not like Egnatia Highway with the huge range of geological environments in order to test that. But in my appreciation, yes, indeed, the appreciation of the failure modes can assist you to the a better selection of the appropriate TBM machine. and not just by a rock mass classification value, which I understand this is a very straightforward and helpful process. There is a very, very detailed work when you select a TBM. So imagine when it is connected with the failure modes, then it becomes, in my understanding, more effective.
Thank you.
Thank you. So if there are no further questions, I think we will bring this workshop to an end. So I'd like to thank Dr. Marinos for sharing sound engineering methods and design approaches with us, and of course Dr. Benardos for educating us further about how sound engineering judgment guides risk management and commercial decision making. It is usually said that one should try to learn something new each day, but I'm quite sure almost all of us are walking away from this workshop with more than one invaluable lesson today. So once again, thanks for the very interesting presentation and further inputs during the Q&A. Also, thanks in order to George for coordinating this workshop, Dimitrios and GTS-YMG for their welcoming response to our collaboration efforts, and most importantly, all you delegates for attending, else we would be speaking to an empty room. Hope all of you stay safe during these times and hope to interact again soon. Good night.
Thank you for having us, and it was a pleasure.
Indeed it was. I hope we meet in person, all of us, in some time in the future. Goodbye.
Bye-bye. Good night.
Take care. Stay safe.